NMR, nuclear magnetic resonance spectroscopy. So spectroscopy, again, we've been harping on this. Andy, is the interaction between what and what?
A magnetic field and...
Well, it could be the magnetic field or the electric field of light and matter, or atoms. So what's the matter going to be with NMR spectroscopy, Brandy? What's the matter going to be? Yeah, well, we're putting in a little sample tube. But exactly what specifically? Yeah, good. Nuclei. What nuclei? Hydrogen atoms. Protons, right? Okay. So you see this little guy. What's this picture trying to say? What is that supposed to be? All right, here's one right here. All right, I don't know. It takes a while to get it going. If I can't get it. I got to wrap the string around and do all that fancy stuff. But it's a gyroscope, right? The center part in here spinning really fast. And that's what I should have wound it up. I was setting up all that other stuff. But if I got it wound it up really good, it would sit in there like this and start spinning, right? But then it starts going like this. And you can't stop it. And that's what they're trying to say here, that this gyroscope, it just starts going around with some frequency. Right? And that is the key to NMR. It's odd, but that is the key to NMR spectroscopy, is that little gyroscope doing this, its axis of rotation, just rotating. Okay. Okay, so that's some general concepts behind NMR spectroscopy. An animation of positively charged particles passing through magnets. Let's see what that looks like. Where is it? Here it is. Okay. Positively charged particle passing through magnets. Okay. One thing that I liked about it is something you probably can't tell. And that's, did you see this guy? It was rotating, and that is key. If he's not rotating, this whole thing isn't going to work. See him rotating? Okay. Here I am. So let's go ahead and get started. We'll just go around and you read one to give your best guess. Start with Brandy. We'll go around and answer these questions. So just go ahead and read it and then say what you think. I'll give you a hint, you can't see it. You can FM 101.9, Kono. Or is it? It's 101.1, isn't it? Radio waves. Radio waves. Whoop. Really long, right? The wavelength around a meters, tens of meters, about as short as they get. Okay, keep going, Mel.
Organic compound consists of hydrocarbons.
Hydrocarbons. What elements?
Carbon and hydrogen.
Carbon. Yeah, good. Okay, keep going.
If you could distinguish...
Well, hydrogen atoms.
Hydrogen atoms are basically what subatomic particles?
Protons, exactly. Hydrogen atom, if you rip off that electron, it's a bare proton, but okay. Now, Alyssa.
If you could distinguish all the protons present in an organic molecule and determine where all the protons are in the molecule, could you deduce the general structure of the molecule? For this reason, proton NMR is perhaps the most common type of NMR spectroscopy.
Perfect. Okay, Andy.
The proton is charged and spins. Can't stop the spin. From physics.
Do you remember that? Remember that? What movie is that from? It's not spin, it's signal. It's from my favorite movie on the planet. Can't stop the signal, Mal. Can't stop the signal. It's the best. No. This was even better than Star Trek. No. Firefly, the movie. Oh gosh, that's the Okay. Can't stop the spin. Okay, keep going, Andy. From
From physics, any spinning charge behaves like a
you had a hint in the movie.
atom.
Okay, so you had the spinning charge in the movie, and notice how it got moved around by the magnets? So magnets essentially push around other
Charges?
magnets, right? Magnets. So by having that charge spin, it behaves like a miniature magnet. This is really curious. I can't think of another field of spectroscopy where the light is the magnetic field that interacts with matter. NMR is pretty much the only one where it's the magnetic field that's interacting with the matter, not the electric field. Okay, we're back to Brandy.
They work with the size of an electron and spinning photon, and a homogeneous magnetic field has a blank energies, which is quite unlike the
Neodymium magnet. That's this guy. So the neodymium magnet placed in a magnetic field. Okay, I can spin them whatever speed I want. There's no blank energies. Right? The idea behind spectroscopy is this idea of interaction between light and matter. That's great. But it all works because of this idea. P-chemers we had the Jablonski diagram. What's with these energies? Can you take on any energy? What word are we looking for? Quantized energies, or there's a lot of words you could put in there. It has quantized energies. That's the most technical jargon you can use. Or you can just say because it has only specific energies. It can't take on any energy it wants. It has a narrow set of energy levels. There's a lot of words you can put in there. Quantized is the best, I guess. It's the most technical, but. So why is that different from a neodymium? Well, geez, you can spin this as fast as you want. You can take on whatever energy it wants. Okay. Oh, I think we're on Mel now. In fact.
In fact, a proton is a homogeneous magnet, has only two possible energies. It's higher and lower energies.
Two possible energies. Can you describe them? Yeah, it would make sense. That'd be a good guess. A higher and lower energy. Okay, I agree with that. Okay.
Would the ground state be the lower energy?
But here's your hint. Your hint is this diagram. So describing them meaning why is one state higher and why is the other one lower?
Because one is in its ground state.
Yeah, you can say that, but. Okay, they're trying to say, what's the N and the S mean? North and south poles, right? And when you have north lined up with north, does it push away or does it attract? It repels, right? Okay, so inside, these are supposed to be our little spinning what? What are these things supposed to be? Those are supposed to be our protons. They're spinning, acting like a little magnet. Okay, so then they put this huge magnet outside surrounding it. Okay, it has a north and a south pole. And it's a U shape. All right, here's one right here. You just bend them, you get a U-shaped magnet. So does it make sense why one orientation is lower energy and the other orientation is higher energy? That's what they're trying to say. Anybody see it? Why is that? Exactly. Do you hear what she's saying? Brandy's saying the higher energy they're repelling. Yeah, north is lined up with north, south is lined up with south. Okay. So those are the only two possible orientations, which sounds completely ridiculous. Why can't you just have any orientation you want? Why? Energies are quantized. That's just how it is. That's how nature is. There's only certain energies that are possible. Here they are. Okay, and yeah, and you can use the words excited state, ground state, but it's kind of confusing. It's easier just to recognize, oh, okay, well, the little spinning magnet can be lined up, or it can be working against the electric field. Sorry, the magnetic field. Okay, so which is the ground state, which is excited state? You can see the ones where they're opposite are going to be the ground state, right? Because they're attracting, it's more stable, lower energy. Oh, I went Alyssa now. Okay, so far.
So far we have noticed the effect of spin on the overall motion of an object. What happens if we spin a bike wheel? Is there any additional motion besides the spin?
Okay, there's the word angular momentum. Angular momentum is, but that doesn't really answer the question. But, well, we should describe angular momentum since you mentioned it. So we take a bike wheel and we spin it. I'm going to spin it in this direction. Okay. Now the reason why it stays in that plane is because of angular momentum. Okay. So, but the question is this is the question. What happens if we spin a bike wheel? Okay, I'm spinning it. Is there any additional motion besides the spin? So here's the spin. Is there any additional motion? That's what it's asking. There is. My hand's keeping it there. Right? Same as that gyroscope. You can't stop it from doing this. And you can, it doesn't matter what the angle is. I can have it at this funky angle, and it's still going to do it. Except look at the frequency. It's a lot slower. Something's going on here. So there is additional motion besides the spin, and you can't stop it. So that is precession. That is precession. That additional motion that they're talking about, that rotation, is precession. You bet there is. And that is precession. Okay? This is precession. That's precession. Okay? Change the angle of it, and it'll even change the angle of that precession. So how did I stop precession? Yeah, I just kind of had to hold it, right? But I mean, if someone's not sitting there holding all these little subatomic particles, they're going to precess. You can't stop it, right? Okay, so you can't stop it. It's going to be there. Okay. It's just like a charge. I mean, something's charged. You can't stop the charge. Okay. So here's here's the questions that refer to these diagrams. So they're trying to say, right, here's your spinning guy. It's going around this way. Okay. And then here's the rotational axis, right? Or that's really the line that's the vector really of the angular momentum that Alyssa was talking about. That's more P-chemish though. We're not really worried about it. But the point is that it's rotating. Right? They're trying to illustrate the same thing here. Okay. What's this B thing doing? They're saying, look, and notice that it's an arrow going straight up. They're saying that's B naught. You should actually have a little vector thing above it. B is the mathematical symbol for, anybody know? Magnetic field. The only way you'd know that is if you really dug it out of the reading, I think. Okay. So you have a spinning charge, apply a magnetic field, and then you see this precession. About the magnetic field, about the applied magnetic field. Either it's going with it or against it, those two possibilities. And that's what they're trying to say down here. Right? So either there's two states, one higher, one lower. Either the little magnet's lined up with the field or it's lined against it. So that's why you have these two states. Oh, I don't know. I'm running Andy. Andy, according to figure 19.1.
According to figure 19.1, a spinning proton has two energy states when placed in a magnetic field. The energy states are separated by delta E equals
Yeah, gamma H over 2 pi B naught or something like that.
where gamma is referred to as the magnetogyric ratio, which is
Blank for different elements.
blank
What would you guess?
different.
Yeah, good guess. Right? Because they should. I mean, you have different elements. They should have different magnetic strengths, right? Different charges and whatnot. So that would make sense. Okay, and then for different elements. H is, Brandy? Planck's constant. Planck. And B naught represents the applied, Melissa? Magnetic field. Does anyone know what the units are for magnetic field? Starts with the capital T. I don't think that's more information you need to know. Okay. A classical NMR absorption. Alyssa.
A classical NMR absorption event would consist of a spinning proton precessing about its axis of rotation, then a magnetic field
Good.
is applied and a spinning proton.
Tips over. Good. Right? Exactly. So that's absorption. It's kind of weird. You know, we like to think of absorption as, oh, I have yellow light, now I don't have enough yellow light. Well, absorption is any light. You absorb it. It's attenuated. So, and light is magnetic field and electric field. It's just odd to be talking about magnetic field is all. So it absorbs this energy, right? The energy goes into flipping it over, okay? But it's still precessing this whole time, okay? And can emit light. What light would it emit? What range? Right? If it absorbed, wouldn't it emit the exact, pretty much the same? Right? Emit the same, radio waves. It would emit it. Okay? So no big deal. And go back to its ground state, where everything's nice and lined up. Okay. Are we on Andy in past chapters?
In past chapters, we said the energy of a photon of light could be written as E photon equals
Well, that's a good PChem question, Alyssa.
1.4.
H frequency, H nu. Okay. Therefore, for a nuclei to absorb a photon and make a transition between energy levels spaced by delta E, the photon energy must exactly equal same thing, right? Okay. So in other words, oh, you already had that answer down there. Okay, in other words, E photon equals H nu, which has to equal delta E, which has to equal that equation that Andy read. So according to the above relation, what must the frequency be equal to of the photon? Well, essentially, just cancel out the what? Anyone see it? Just cancel out the, yeah, cancel out those H's and you've got it. So it's pretty much gamma, what, a B naught over magnetic field over 2 pi. Oh man, if you know this one, you get brownie points. This frequency is referred to as the, I think this guy, you've heard of this name before. He's an author. I think he writes these lovey-dovey cowboy books. L'Amour. Am I just dreaming this? I don't know, it sounds familiar, doesn't it? That doesn't sound familiar to you?
Larmor.
Larmor. The Larmor frequency. Okay, so let's, I don't know. Brandy, you're on this one. The frequency is referred to as the...
Oh, hold on, I'm still reading it.
So this frequency, yeah, let's see if you can figure it out. Good guess. Yeah, I think that's true because the frequency of absorption is going to be the same as the frequency of emission. That's true. There's two correct answers on here. It's precession. It's precession. That's what I was hoping that you would say. I never even noticed that, but I think you're right. But precession is what I was looking for. But emission is right too because look, they're exactly the same, whether it's absorption or emission. Okay. Terminology and general concepts pertaining to FT-NMR spectroscopy. Starts out, Melissa, with what does FT-NMR stand for? Yeah, how do you spell it? Good. Fourier transform. Yes, perfect. Nuclear. Magnetic. Spectroscopy. FT-NMR. Okay, with FT-NMR, instead of a continuous bombardment of RF energy, ooh, we should have had a question there, Alyssa. What's that? RF. Oh, there's a lot of RF. What's RF? Well, you have a guess? Anybody? RF. Big R, big F. That's just how they write it. But they're abbreviating. They're already getting lazy. What's the region of electromagnetic spectrum? That's radio frequency. That's it. RF is radio frequency. So instead of a continuous bombardment of this radio frequency, right? Because remember, what are we talking about? We have to shine light on it, right, to get it to flip over. We said it's this frequency, and this is the RF right here, right? The radio frequency. The RF energy is pulsed. Okay, looks like there's about 10 microseconds between pulses. Okay. So you can, and actually inside that pulse is a sinusoidal wave. Okay. Nuclei, let's see, we're right here. So this RF frequency is pulsed, Andy. Nuclei absorb.
They absorb the RF energy, then emit RF as they return to their ground state. This emitted signal is referred to as the
Oh, that's a tough one.
FID.
Yeah, we just call it FID. Oh, that's a good one. That's a GC, flame ionization detector. That's true. This is a hard one. Decay. That's a hard one. That's a really hard one. Okay. But you've seen this. I don't know if you've done the NMR upstairs with an organic or something, and there's this plot, and he had this red line that went like this, and it went down to nothing. That's your free induction decay. That's your ugly signal. That's your signal decaying over time. All your information is in there. All the frequency information is in there. And that's what the Fourier transform is going to do. It's going to go from the time domain to the frequency domain. You get what frequencies are in there. Okay. So you've got this absorption emission process going on. Yeah, but the emission is what gives rise to that decaying signal, right? It's going to have a lot of decaying emission at first and then just dies off. a single FT NMR event description. Let's start in A, Brandy. In A, blank state. Ground state, perfect. Okay, Mel.
B naught is magnetic field.
Yes, okay.
Yes.
Is it implied the entire time? Does everybody agree? Yes? Yep. Because it never disappears, right? Look at that. Okay.
In B, C, and D is a second magnetic field B1 applied. Yes.
Yeah, can you see it?
Yes. And what effect does it
Whoa, whoa, slow down. I'm just trying to make sure everyone sees it. Right? Okay. Keep going. What effect?
What effect does it have on the orientation of the spinning nuclei? Just causing it to rotate.
Yeah. It's like, do you see, can you imagine? First, do you recognize what this circle is trying to represent? Right? That's this precession idea, right? That's go way back over here. Right? That's this thing they're talking about. That path of precession. Okay. So it's spinning around like that. Okay. And your answer was what, Alyssa? So it's rotating right here. Now it's going here. It's caused it to, I think you said the word, flip over kind of. Didn't you say that? Yeah, I think you said that earlier. Kind of causes it to flip over. It's still precessing. Remember, you can't stop the spin. So it's still precessing, but now it's just, it didn't go, and notice how it didn't go all the way down against the applied magnetic field. It just went halfway. So they call that a 90-degree pulse. They could have had it go down all the way, but there must be some reason. It must be cleaner, faster, easier just to do it this way. This is what they do. Okay. Plus, it's also the direction of that the applied magnetic field is. It's applied perpendicular. Okay. Andy, in E. Where's E? Here's E. Yeah, but first see if you can see what it is. Okay. B1 equals what? You see it? Zero. They shut it off. Okay, now keep going.
The magnetic field returns to the ground state. As it returns, it's something RF energy. I think it's
Emits. And that's typo, right? They're talking about the spinning proton, the spinning nuclei. Right, the spinning nuclei returns to its ground state. I gotta fix that. Okay, Brandy, the frequency of RF. Starts with an L. That Larmor. That frequency of precession. So, with what we know so far, what good is this? All these protons, they're all protons, so shouldn't they all have the exact same Larmor frequency? So what's the point? Ooh, you get more signals, more protons? There's got to be more to this. Okay, now, Mel, keep going.
Once the FID is obtained, a Fourier transform is applied to the FID signal to convert the FID from the blank domain to the blank domain.
is which
The
one?
time domain to frequency.
Perfect. So here's time, right? Your decaying signal, there's seconds. And then it goes to frequency. And frequency is going to be a big deal, because if you go to, and we're going to see this, you go to all these little charts, and we're kind of getting ahead of ourselves, but everything's lined with frequency, all the different protons. Oh, here it is right here. From the frequency domain, from the frequency information, we can determine the chemical environment of different nuclei. Okay. So they must not all have the same Larmor frequency. Even though they're all protons, we haven't finished the story. These protons, their Larmor frequency must be dependent on what's surrounding them. We're going to see. Okay? And there's big chart. Let's see. So from the frequency information, we can determine the chemical environment of different nuclei. In this case, we're all talking about protons. What's the chemical environment of different protons? Is it next to a methyl group? Is it next to a carbonyl group? Is it what's its chemical environment in that molecule? And even get the number of them that are like that are in that particular area. Like a methyl group has 3, for example. Why do protons in different chemical environments absorb and emit different RF frequencies? Hint, what was the equation for Larmor frequency?
Is it the mu equals gamma over 2 pi magnetic field?
Here it is right here. What could change in there? Yeah, I mean, the magneto-gyrec ratio, that's going to be a constant for different elements. It's going to be different for different elements, but they're all protons, so you can't mess with that. Can't mess with 2 pi. So what has to be happening here is B naught has to be changing, the magnetic field. But how can that be changing? You've got this big, looks like there's a big permanent magnet in there. So you're telling me different protons have a different magnetic field, but it's all the same magnet.
So protons can attract it easier than others? Or something?
You're getting there.
Because of the chemical environments, like depending on like what carbons or what carbons and different like hydrogens. Like you were saying earlier, right? With the if it's a methyl group.
Yeah, but what could, okay, pretend you're a spinning little proton, okay, and you feel this push. Now, you're doing the old precessing thing and everything. You're feeling this little push because you have an applied magnetic field, right? And you're being pushed over. What could strengthen or weaken this magnetic field that you're feeling? Pretty much only one thing that we know of. Other magnets. Other magnets are the only thing that's going to influence what you actually feel, right? Because other magnets could be pushing you or whatever, right?
Hydrogen atoms?
The other, what atoms? Protons.
Like on that.
The other protons. They're acting like magnets, and they're going to influence what's going on. So they're going to, some protons are going to feel a much stronger magnetic field than others. We're going to get into this word called shielding. So I think that's what's coming up next. Let's see here. So here they are. Environmental effects for proton NMR. There's 2 types. So how can there be this table of different hydrogens giving different Larmor frequencies? The environmental effects. I guess we're on brandy. Environmental effect type number 1, chemical shift.
Different protons and molecules feel different applied magnetic fields because electrons shield the
Good.
applied magnetic field. So protons in a part of the molecule with a lot of electrons usually feel a higher or lower.
That's, yeah, what would you guess? It's actual shielding. I mean, you kind of like lead wall. Yeah, it's going to be lower. In comparison to protons that are in an environment with less electrons about them. Okay, Mel. If chemical shift.
If chemical shift were the sole environmental effect, we would expect to see individual peaks in all NMR spectra. The individual peaks would indicate different chemical environments, and the bigger the peak, the blank protons will be present in that particular chemical environment.
The more.
Yeah, exactly. So if this was the only thing that was happening, it would be really, you know, you could see, oh, I have this peak right here, right, at this frequency, you see what that frequency is, right? And they call it ppm, and they have shifts and whatnot. But you look at the unit, we'll worry about that later. You look at the frequency, match it into this table, and you know what type of proton that is. And the bigger the bigger the peak, oh man, I have that many protons that are of that type. Okay, but things are a little more than that. Spin, spin, splitting, Alyssa. Magnetic moments.
Magnetic moments of protons interact with each other. Since magnetic moments interact with one another, we don't get individual peaks for different chemical environments. Instead, we get split peaks for different chemical environments. This study follows the N+1.
Oh, I should have left a blank in there for 1 or something. See if you guys remembered that. Right? Okay. Let's take a look at ethanol. Now I'm saying, what is the chemical structure for propanoic acid? It's not ethanol. That's okay. Go ahead and draw the structure for propanoic acid. Wow, what am I doing here? I wonder if I messed this up. I was halfway working through this. I'm asking about. It should be okay. I wonder what I was after here. What if I skipped something? Let me just check something quick. This is day 17. Man, we're about out of time here. How much is left? Ah. Yeah, we're not going to finish today anyway, right? So we're going to stop here, and then we'll come back. That way I can see what the heck is going on, too. And we'll come back on Wednesday.